Hello, welcome to the fifth class session of quantum topology training CNPTL course. This is Shawik and fifth class session. Um, and first, let me introduce myself. I'm Shawik, and right now I'm doing my PhD from class in mathematics. So first, let me know whether I'm audible or not. So one student, namely Avinash, is there. So Avinash, can you please tell me whether I'm audible or not? Avinash, can you please tell me whether I'm audible or not? And is my screen visible to you or not? Avinash, can you please tell me whether am I audible or not, or is the screen visible to you or not? Can you please confirm? Okay, it seems that anyway, no problem. Let's continue. Oh, so I hope the screen is visible to you and and I'm clearly audible. Okay, if not, then please stop me and ask. Well, so let's start. So, before starting further, let me know. Do you have any question from the previous session, or do you have any question from the assignment, or do you have any questions from the third class? If you have any question, please ask. Please try to utilize this session because this session are meant to be problem solving. So please keep, try to solve problems as much as you can. So if you have any question, please ask, or else I can go for the something new. So it seems that there is no question, so let's start today's new session class. And so in the separation exam, there are many problems, many exercises, but there are two very important theoretical separation axioms, namely Urishan's lemma and Urishan's lemma and Urishan's metrization theorem, T's extension theorem. So these three important things in quantum biology, which actually makes a breakthrough in scientific theory. So let's start one by one. Okay. So well, let's start with for the Orishan's lemma. So what the so there are basically three. One is Orishan's lemma, another is Orishan's metrization theorem, and third one is Tiered extension theorem. Okay. So basically these three are very important theorems. But we shall see the proof. But right now the looking at the proof is not as important because solving problems is more important to follow the understood proof right now. Okay. So first we shall state the statement of those two theorems, try to solve problems, and then we shall go back to the previous questions, and then we will again try the problem involving all these things. Okay. So let's establish Wilson's lemma. So what does it tells? It tells that let capital X be a normal space. Okay. Let A and B be two disjoint closed subsets of capital X. Let A comma B, let the closed interval AB Okay, leave it. Let's modify it. Then there exists a continuous map f from what to where x to close interval 0 to 1 such that f of a fully 0 and f of b is fully singleton. So these are the statements. So what is the statement? Capital X is a normal space and A and B, A comma B, these are two disjoint closed. These are two disjoint closed as your capital X. Okay. Then there exists a continuous of little f from capital X to close 0, 1. So f of A is equal to singleton 0 and f of B, singleton 1. Okay. So this is the Orician's lemma. So this is the very important thing. And after Orician's lemma, there something is called Orician's metrization theorem. What does this tell? This tells that every regular space X with countable base is metrized. So every regular space X with countable base metrized. This is a metrized that is equal space a regular that is as so regular space means what? So in the last session we have seen regular space means a single point and a closed set not containing the closed single set and the single point or closed set can be so that is regular space that is and second countable plus metrizable. These are possibly a great breakthrough in the immediate things regarding the triation of logical space. And the third theorem in this row is the following one. Third theorem in this row is the following. The theorem is it is the extension theorem. What does this tell? This tells that let capital X be a normal space and let A be a closed space of X. Then first thing is any continuous map of capital A into close interval a comma b of r can be extended to whole of x continuous. So that is if you have some map from capital A to for A comma B, then the space capital A, the mother space is closed, is a normal space, and capital closure space, then the continuous map can be extended to capital X continuous. Okay, this is one thing. And second is any continuous map of A into what may be extended to continuous map of all of x into y. So there are only two differences. In the first statement, the map is from capital A into closed. Again, in the second expression, the map is from capital A into whole of R. That is the two things. So first is oh. So the first point is that if capital A, I mean the capital close house, if the map from capital A to the so that map capital A into R can be capital A to I mean capital A close to AB, then it can be smaller. Like instead of capital A, we consider the whole real line. The map from capital A to capital R can be extended from both of them. That's there is nothing extra. So these are three steps. So first one is what? First one Audition's lemma. Second one is audition metric. Third one is T is extension. So now, so the three instruments now. Okay. So now let's try to solve some problems. Okay. So hi, sorry, possibly actually the message did not come to the screen, so I was unable to look at the text message. So you are asking to explain the product to leaders of India. Okay, sorry for the late realization. Well, one minute. So was there any option to okay, okay, Avinash. So well, I will explain it soon. Okay, Avinash, I will explain it soon. Okay. Right now we are in section, so those things after going to those things as I explained, product is by working exam. So the first exercise one. Show that a connected normal space having more than one point is on. Well, before going this, actually first solve this problem. Show that connected metric space is show the connected metric is unbounded. So first try to solve this problem. Uh, Try to show the cannabis module. Okay, then after solving this, go to the first. Okay, think about it. How you can show the cannabis. So look, only you can. So look, so directly it is obviously not possible. I expect to show something uncountable. So one possible way is that if you can consider function to the matrix to real line, whose image is uncountable subset of real line, then you can say that the domain is uncountable. So try in that direction. Think about it, or else I shall think about it and let me know. I'm going to Well, so it seems that. So let's check. Well, so so no problem. So let's first try to see that how to do the same with the metric space. Okay. So look, of course, as I've already told you, the putting the same in metric is not of direct. So how to do? So so obviously one thing, kind of metric space with more than one point. This is obviously there. So let capital X be such. So since it has to more than one point, so let capital X not belongs to capital X. Okay. Now define a function f capital X to R by x goes to d of x comma x naught. D is the distance function of the metric space. Distance function capital X. Okay. Now since y belongs to x with y not equal to x, so this implies what? This implies d of xy is not 0. And of course that this is a continuous function. Why? Because dx naught minus dy y naught less dx y x naught less than equal to dx y o. So this image f number of events image f greater than equal to, but image f connected since why connected, because f continuous plus capital is connected. This implies what? This implies image f uncountable. Okay. So that is it. Let me know, do you understand the argument? Let me know, do you understand the argument or not? So let me repeat the argument at least for whom, for them who have not seen this argument previously. So this is actually very quite nice trick to show something uncountable. Okay. So the technique is the following: we construct a function from capital X to real line image uncountable. How to do that? So we are considering the map x goes to distance between x and x naught. This map is only continuous. This map image contains two points. One is zero, another non-zero element because it contains more than one point. Okay? So, but in real line, connected say with more than one point is uncountable. But image which is subset of real line is countable. That's all. So that is that window. So that's why so of course so this is what so x uncountable. Now so here we have construct you prove the given matrix uncountable by using primary construct function. But now go to the first problem. Why we need to show that connected normal space having more than one quadrant. Now then how to, of course immediately we have the liberty to construct such a function, but in case of topology we can't do it, right? How to do it? Think about it. So basically we somehow need to use some construct some kind of function. Okay. So how to get that function or from where to get the function? Well, so now so first go to the question itself. So what does it really? So connected normal, it's a normal space, okay. So since the space is normal, so we can now use the normality or techniques. So now, so that is, so that why, so that's why, since it's the normal, so we can use the Audition's lemma, right? The first lemma. So how to use that? Of course, in the same instance also, it will be connected metric space with more than one point. Oh, that's there already. So let consider 2 points. So let x not y not belongs to x, y not. Now, obviously, singleton closed. Since a regular space, so normal space for the house of these are closed. So there exists a continuous function f from x to 0 comma 1 with f of x 0 is equal to 0 by the 1 by Lucius lemma. So this is so basically the number of elements in image f to image f substituting a line and x connected. So this imply image f connected. So this implies image f uncountable. So basically, we have 2 points x naught y dot capital X, and so those are singleton and closed. Now we can find a continuation f from x to the 1 with a from x. Right. So now the image. So this does what? The image f contains more than 2 points, but image is subset of real line. And image of connected because it's connected. So in real line, the only connected subspaces are as a single number in global. So anyway, this is countable. So of course, so capital is uncountable. By the way, one may ask that since this process is applicable in normal space, so now since metric normal space, so can I use that trick? And yeah, of course, you can use the trick. But the point is that since already metric have so many advantages that not required. So, so that is the okay. So, Avinash, now let's one. Well, so Avinash, so now let's get back to the question. So, so you have all the product rule in not in the flow. Let's let me write the argument again. Okay, wait. So product of two Lindelof space need it's not product rule is not. Okay, so for that, so R with lower limit topology is Lindelof. But RL2 is not. RL2 is known as a surgeon free plane. Okay. So now look into the argument properly. Okay. So I was thinking about something, some easy argument, but it's not coming. So let's back to this argument that we see in the last session. So let me repeat again the same argument here. Okay. So so first in real life, consider this following line: x comma minus x belongs to R. That is, if we draw pictures, in picture it will come like the following. So this line is x comma minus x. So this line is L. Okay. First observation is the following. First observation, this L is closed in R. The first of the L is closed in R. So how to do this? For this you can use sequential argument. Why? As it is first countable. So after doing this thing, so that is L is closed. So RL minus L is open. Okay. So basically we need to show not linear. Means what? We need to consider open cover which does not have any count to it. So in this first we need to consider open cover at least, correct? So now we need to cover each point of the line capital. But how to do this? So now, so suppose we have some point x comma minus x here. Okay. Now we are making some open subspaces around the points. So this subspace is like this. Okay. So basically we can like that x plus epsilon, third bracket x comma x plus epsilon cross third bracket minus x comma x plus epsilon, something like that. And RL minus it we can cover each x comma minus x of L by x comma x plus epsilon cross minus x comma x plus epsilon. So in that case, RL can be covered by the scissor form x comma x plus epsilon cross minus x comma x plus epsilon. That goes to 0 union L. Union, sorry. Union RL minus L. Okay. So RL is equal to x comma x plus. So okay. So this is the thing. Okay. Now if now this is open cover. Okay. Now if this open cover now observe if this open cover now if this open cover has countable subcover, then now if this open cover has countable subcover, then L subset of countable subcover of this portion is called as V, the countable subcover. But it is not possible. But look, it's not possible since each state of the form intersect L. So that is the main thing. Intersect the line L in exactly one point. And of course, a line is uncountable. Okay. So that is the so of course this open cover does not have any countable subcover. So that is our argument. So basically let me repeat the argument again here. So the line L is closed in first the surgery. So first that RL cross RL is not Lendala. So first we have observed that RL is countable. Sorry, Lendala, but it's not Lendala. We need to go. First we observed that we have chosen the line y equal to minus 6, and first we have observed that line y equal to minus is close surface of RL cross is close surface of surgery line. The rest of the proportion is open. Now we need to cover each point of origin point of line x comma minus x set, and we took the open basically R2, and then we check that this is the open the line is exactly one point, and the line contains so the line cannot be covered not by counter prediction basically covered so this tells that so RL2 is not so Avinash is here. Avinash, let me know. Are you there? If yes, please let me know whether is the argument is clear to you or not. So yeah, so that is so this is the thing. Okay, so I hope it is the argument is clear to you. If not, you can stop me and ask questions. Okay. So since you are not giving any answer, so if you please go through the argument and for the next section. Right now, let's go to exercise. Okay. Well, so the now the next question goes as follows. show that connected regular space. So that connected regular space having more than one point is uncounted. So for in order to prove this, you need to use that Venetian metrization theorem. Think about it. I shall be back in a few minutes. Okay. Think about it. Try to solve it. How about let me know, are you going to get any kind of idea how to solve it? How about so so here it should be connected regular space having more than one telephone. For that, I have told that we need to what? We need to use Urishan metric theorem. What Urishan metric theorem tells? Urishan metric theorem that every regular space is countable. Regular space is countable basis. Triads, correct? Regular space is countable matrices. Now, so suppose we need regular counter base. So now we shall try to solve by contradiction. So let its counter. So of course, since the space is countable, so we have a countable places. Definitely, there is nothing. No going to the countable places. Now, since it is regular, so by Urishan's metrization theorem, it is metrized. So it becomes connected metric. It becomes connected metric space. It becomes a connected countable. So it becomes connected countable. So, so that's it's not possible. Why? Sorry. So there is some issue with the camera. So I shall rejoin the session. Okay?
So there is some issue with the camera. So anyway, so let's continue. So by collision metrization theorem, so it becomes connected counter matrices. So that's impossible. Why? Because since due to previous problem. Now, so this tells that connected. It says that regular space having more than one point is now. So is the thing. So now let's go to the next problem. Power. So so we have already seen there are two theorems, namely V6. What's that? So there are two theorems, namely it is electricity theorems and collisions. And collisions, and collisions level. Okay. Now, now we shall some. The next question follows that basically these theorem collision lemma are basically same. So the following exercise. If the extension theorem implies collisions. So how to if the extension theorem implies collisions? So, so of course, in order to prove collisions lemma, in order to prove the collisions lemma, we need to do what? We need to start with uh, closed disjoint surface, right? So let A and B be two closed disjoint surfaces. Okay. So let A and B be two closed disjoint surfaces. Now we need to use this collisions lemma. The T section we need to uh, show, show, show now look. So of course, so A union B is closed. Correct. Now we need to make a function. Now define a function f where A union B to comma 1, sending A equals 0 and b equals 1. If continuous, since if restricted to A, if restricted to B, both are continuous. And at any exception. Okay. So this simplest bottom. So now, now you can extend A by let's say extension here. That is F tilde from X to 0 with F tilde restricted to A and B. Let F. Okay. So I mean, so this is and clearly, if there is the following property, if tilde of capital A is equal to 0 and if tilde of capital A is 1. So this is what the relation. So this is so this is right. So this is it. Okay. Now, so till now, do you have any problem or a doubt? And Abhinash also, if you have any doubt, please ask me. Please ask me. Because this session is actually for problem solving session. So please try to make a systemization as much as you can. Okay. So this is it. Now. Well, now there is next exercise. So let capital X compact house. Show that capital X is factorizable if and only if capital X has countable bases. So show that capital factorizable if and only if capital X has countable bases. So how to do that? So think about it, take your time. So, or else I will solve it. So the statement goes as follows: that compact household space, then capital, the space in triangle if and only counter basis. Now try to think which theorem is to be which theorem is needed to be applied for such situation. Think about it and try to solve it. Okay. So okay. So let me solve it. Well, so look, it's a compact household space. So let capital X in class. Then since X is compact household space, X has a countable range subset. Now question is why? A space, if it is a house, compact house draws, then it must have a countable and subset. So I'm leaving this right now for you because it is expected that you have done this trigonometry support. If not, think about it, you try to solve. If then also it is not done, please bring me to the next session, okay? So since it's a compact house drum space, so it's a countable dense subset, that is what? That is X is what? X is separable. And we know separable metric space is same countable, and separable metric space is second countable. Okay, that's all. So basically what we've done. If X is metrizable, then since X is compact house space, so it's uncountable itself. So try to understand why it's possible. And now since it's separable and symmetry is the same countable, so that's why so it has so definitely. So it uh, okay. Conversely, so let X be second. Now now since it is compact plus alpha plus so X is also so X is also and Nishan's metrization theorem tells that Nishan's metrization theorem tells uh, regular space countable metrization. Regular space with countable base is metrization. So both direction. So both direction done. Okay. So basically, if you observe the question carefully, then actually this question is a criteria of a compact house with specific difference. Okay. So that's why see so not so this is not only just an exercise, but this is also very important facts. Now, now well, there are some also some intrigues here. So let's try to uh, so question three. Question is as follows. Let capital size be a topological space. If y is as said, we say that y is a graph of said if Eric is continuous R from Z. Oh, so reverse direction Y. So wait, so let's start. So first question: if X house draws Y, um, so this is the first question. The second question is that let S1 be unit circle so that S1 is retract of third question is let A be a 2-point set so that A not trivial problem. Okay. So there are three questions that we are right now trying. We are right now going to solve. Okay. Think about it and first think about it, try to understand how it works. Skills we are here for this problem. Well, so what the first question? First question, goes as follows. First question is that if the given temporal space of house draw, then retract with closer. How to do this? Okay. So, look. So, y closed which is equal. So we need to show y closed is equivalent to saying z minus y open. Okay. So choose z not belongs to z minus y. That is z naught does not into y. This implies what? The retraction of R then not equal to z naught. Correct. Now, since given bigger space as house stars, so there is open set U containing R z naught, V containing z naught, U, V both in such that U intersection. Okay. And these two things, what this term gives, Z not belongs to R inverse U intersection V. Correct. Now, claim is the following. Claim R inverse U intersection V, sorry, intersection V is a subset of Z. Okay, so proof, how to prove this proof. So suppose that some Y belongs to Y with I'm basically contracting R intersection. So these implies R of Y belongs to U and Y belongs to V. Correct. But R of Y is equal to what? Y. So this implies what? Y belongs to E intersection B. It's a contradiction. Contradiction. Why? Contradiction by choice of either the house reference. Yeah. So that's that one. So what? So this tells what? So this tells that R inverse U intersection is absolute minus Y. And this plus to C. Okay, so this implies what? This implies, and of course, this R inverse intersection is open. So this Z minus Y is open. So this implies Y. Okay, so these are open. So look, basically we have done nothing. We simply first prove that basically we first simply prove that that y complement is okay. For that we have to choose some z not belongs to that's y, and so that will give r of z not. Z not. So since it is house dot, so their existent u belongs to r z not and okay, Abhilash, can you please tell what you want me to repeat? Can you please tell what do you want me to repeat? Avinash, can you please tell what do you want me to repeat? Well, so it seems that Avinash is not here. So anyway, so let's continue. Okay. So this implies what? This implies y is closed in seat. Okay, so that is the thing we want to go over. So this implies what? So this implies that retract of a house dog space always, retract of house dog space always true. So this tells what? This tells that retract of space is always true. Somehow. Okay. So this is the thing. And the things that Ovinas has responded anyway. So let's move on. Next problem. So the second problem was that what? And if the exponent units, we need to show that the unit circle is a retract of active lines. Okay, so how to prove this? I said back. Well, so let's uh, okay. So the retract of house is always closed. So this has been done. Okay. Now let's go to the next question. Second question was that is on so in the second question we need to show what? We need to show the unit circle, the retract of one. This is what we need to show. Okay. So basically we need to do what? We need to construct a function little f format where R2 minus singleton 0 is 1 with If restricted to unit circle is identity on unit circle. So how to make a function? So obviously, f of x goes to x by naught. So this will do the job. Okay, so there is nothing to do with it. Question number 3. So question 3 was what? It was that ha. So question 3 tells that suppose A is a 2-point set in R2. Show that A is not retract of R2. How to do that? Well, so for next question, I seem to be unable. Wait, so let me. Well, so so the thing is that since we have a capital A which is a double term set, and we need to show this is not a retract. So suppose capital A is a retract of one. So that is what there exists a continuous map R from R2 to capital A. So when R restricted capital A is equal to identical capital. Okay. But is it possible? But it is not possible. Why? As R2 is equal to A disconnected, but this will be connected. So such a thing is not possible. Okay? So that's why double term set cannot be retractified. Okay, indeed, this can be modified. Indeed, any countable subspace of R or N cannot be retracted. So this is the modified version. Okay, so check this very chat. Okay. So Avinash has one question. It seems that mic. It seems that his mic's not working. I don't know that. But anyway, so let's get on to business. That he asked that, why the metric spaces? Why? Why the metric normal? Well, let me explain it again. Okay, so the proof is not difficult, but it's quite technical proof. So of course you have to practice a lot in order to get triple this type of proofs for writing the exams, for instance. Okay. And anyway, these things are in the competitive exams, so you need to really practice more and Well. So, Avina's question is that the metric is normal. Why? Why metric space is normal? Solution. One range. So, let's so for normality we need to start with the disjoint closures, right? Well, so for normality, what you need to we need to start with closed disjoints first. So let A and B be two closed disjoint classes. Right. Okay. So for each A belongs to A, we can choose epsilon greater than 0 such that the all B A comma epsilon A it does not intercept B, and for each B belongs to B, choose epsilon B greater than 0. So now define usable union of BA epsilon A by 2, usable union B of epsilon A by 2. Then of course, then U or V are open sets containing A and okay, with A intersection by A. Since if some set belongs to A intersection B, then Z belongs to 3A comma epsilon A by 2 a b by epsilon b by 2. For some a belongs to a and b belongs to b. Okay. So this does what? D of a comma b less than or d a comma z plus d z comma b less than or equal to epsilon a by 2 epsilon b by 2 less than or equal to max epsilon a epsilon b by 2. Okay. So if suppose this is epsilon b, suppose, then what? Then this will tell that d a b square of epsilon b. This is a what? A belongs to b of b epsilon b. This implies what? A intersection b of b epsilon b not. So that's a contradiction of choice. Contradiction. That's why every metric space is normal. Okay. Well, there is really nothing complicated here. Just you need to work around with all those. Well, so basically we need to choose some open ball and closed ball and with epsilons very clever. If it is, so that's it. So there is okay. So Avinash is clear to you. I hope Avinash, it is the argument is clear to you. If not, you can ask me in the next live session. Okay. So well, so so in today's session, so this session. So in the next session, we shall start with mainly solving problems. Okay, and in next session or day after tomorrow on the next to next session, we shall start with those pending proofs. Okay, those pending proofs we shall see in the next session or next to next session. So any doubt you can ask me now, or you can ask me now, or you can ask me in the next live session. Okay. Thank you. I will leave the call.